Hey, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video in which I will review index laws, exponential growth and decay, and finally similar triangles, all three of which will be on next week's in-class project. So how does an in-class project differ from a test? Well, normally in a test, what we do is we ask you heaps of different questions that don't relate to each other, and each question is supposed to assess a different skill. For example, in your last test, we asked you a question assessing whether or not you could graph a line that wasn't in the form y equals mx plus b. Another question assessed whether or not you could add together algebraic fractions, and so on. So in an in-class project, rather than having a different question for every single one of the skills we've gone through in class, we're just going to take some of those skills and see whether or not you can apply them to real-world situations. So the focus of this in-class project will be applications. So there's going to be fewer questions, but each question will be longer. It'll have more parts. But you can still prepare for this as you would for a test, because, of course, we can't apply skills in an in-class project if we don't have them in the first place. So your preparation is just to make sure you have the skills that I go through in this video, and if you have them, you will be able to apply them in the in-class project. So let's get to it. We'll first look at index laws. So hopefully you know by now that if I have something like a to the power of b, I call a the base and b the power or index, hence the name index laws. So the first index law is that if I multiply bases together, I keep the same base and I add together the powers. So an easy example, x to the power of 7 times x to the power of 5. What you do is just keep the same base and add together the powers. Easy as that. So for a harder example, I'll show you one where there are different pronumerals and also numbers. So let's say I have 4x cubed y squared z times negative 6xy to the power of 5, for example. So in this situation, you do the letters and the numbers separately. So 4 times negative 6 is negative 24. So I'll now do the x's. So x to the power of 3 times x, keep the same base, add the powers, because x and x to the power of 1 are the same. So y squared times y to the power of 5, keep the base, add the powers, and there's also a z in the first term. So that is my final answer. All right, the next index law. So this time, instead of multiplying bases, we're dividing bases. So if you divide the bases, keep the same base and subtract the powers. So an easy example, if I have x to the power of 9 divide x, I keep the same base and I subtract the powers. Remember, x and x to the power of 1 are the same thing. So again, for a harder example, I'll use numbers and letters. Sometimes you'll see the division written as a fraction. So let's say I have something like 12x to the power of 7y over 20x squared y. Okay, so we can simplify the numbers separately. So 12 over 20 simplifies to 3 over 5. Use your calculator if you're stuck. The y's cancel out because they both have the same power on top and bottom. And I'm left with x to the power of 7 divide x to the power of 2. Keep the same base, subtract the powers. That is my final answer. So the rest of the index laws in some way or another follow from one of the first two. So if I'm raising a power to a power, so here, note I've got 2 powers, keep the same base and multiply the powers together. That just follows from the first index law. So let's give an example. If I have x to the power of 11 to the power of 4, this time I'm not going to add the powers. I'm going to keep the same base and multiply the powers together. So I won't do a harder example for this because harder examples will involve other index laws, and that's what I'm going to go through on the next slide. So the next index law, as long as a is not equal to 0, then a to the power of 0 equals 1. So that kind of means 0 to the power of 0 is actually undefined, but 1 to the power of 0 is 1. 7 to the power of 0 is 1. Negative 3.27 to the power of 0 equals 1. So I've given you a few examples of that already. Sometimes you might see something like 4 to the power of 0 plus 1. So that would be 1 plus 1, which is 2, because we have to do raising to the power first in BODMAS before multiplication, addition, or anything. The only thing that comes before raising a power is brackets. So for a harder example, I want to make sure you know the difference between these things. So let's say I have 2x all raised to the power of 0 and then just 2x to the power of 0. So we're going to assume in both these examples x is not equal to 0. So the first one, I'm raising everything in the brackets to the power of 0. It's just 1. The second one is 2 times 1 because I have to do this first. So 2 times 1 is just 2. All right, the next index law. So if I take a product and raise it to a power, the power of the product is just the product of the powers. I raise each thing in the product to that power. Okay, so for example, a lot of people get this wrong. If I have something like 2x to the power of 4, what they get wrong is they remember to raise x to the power of 4, but they forget that 2 must also be raised to the power of 4. So the answer here is 16x to the power of 4. So make sure you don't fall for that mistake. Again, for a harder example, I'll show you on the next slide because I'll do one that involves more than one index law. So if you're raising a fraction to a power, it's pretty simple. You just raise the top, to the power of c, just raise the top to the power and raise the bottom to the power. So for example, if you have x over 3 to the power of 3, raise the top number to that power, raise the bottom number to that power. Again, a harder example will be shown on the next slide. So these are all ones you did in year 9. The new one that you may not have done last year is negative powers. So if you have a to the power of negative b, you just move the negative power to the bottom of the fraction and write it with a positive power. So this probably doesn't make a lot of sense. A lot of people think if you, say, raise 2 to a negative power, the answer should be negative, but that's not true. If you raise a positive number to a negative power, the answer's still positive. It actually follows from some of the index laws above. So the reason for it is just to fit in with the other index laws. So let's do an example. So let's say I have x to the power minus 5, and one thing you might commonly be asked is write this with a positive power. So all I do is move it to the bottom of the fraction. Now it has a positive power. So for a harder example, you just might have heaps of things to contend with. So let's say I have something like 2 over 3. We've got q to the power of negative 7, r to the power of 4. So if you have something like that, everything with a positive power goes on top, and then the thing with the negative power goes to the bottom with a positive power. So on the next slide, I'm just going to do a few examples where you have to use more than one index law. So please pause and copy this down if you need. Okay, so let's look at an example like 3x to the power of 4 to the power of 3. So we have a product here and also power to a power. So I have to raise 3 to the power of 3. Now to raise x to the power of 4 to the power of 3, use the power of a power rule. Keep the same base, multiply the powers, and I'm done. So let's have something like 2x to the power of 4 over 5y to the power of 5, and I'm going to raise this to the power of 3 as well. So I'm going to raise the top to a power of 3, so I need to raise 2 to the power of 3 and x to the power of 4 to the power of 3, just like I did in the previous example. Now I raise the bottom to the power of 3. 5 cubed, and then y, keep the same base and multiply the powers together. I'm just using the power of a power rule to get that y term there. So let's look at one involving negative indices. So in an example like this, I have to do the brackets first. It was just in this example and this example, I couldn't simplify the brackets any further. Here I can. So 2 over 4 is just a half. Now, x squared divide x to the power of 6, keep the same base and subtract the powers. So I've got to raise that to the power of 3. So that means I've got to raise everything in the brackets to that power. So what I would do, a half to the power of 3, x to the power of negative 4 to the power of 3, again, I just multiply the powers because it's the power to a power rule. Now, if I want to write this with a positive power, all I do is move the negative power to the bottom of the fraction and write it with a positive power. There, I'm done. So now I'm going to go through exponential growth and decay. So let's first have a look at what is going on here. We'll look at exponential growth. So let's say I invest $10,000 and it's going to increase by 5% per year or per annum, like I'm getting 5% interest. So after the first year, I'll put Y1 for year 1. So hopefully you know that to increase 10,000 by 5%, I just go 10,000 times 1 plus 5 over 100. The reason I can do that is because increasing a number by 5% is the same as finding 105% of the number. This number here in the brackets is 105% of means times. So if I increase 10,000 by 5%, I now have 10,500. Okay, so you can see my investment's gone up by $500 in the first year. Now in the second year, I take the amount I had, 10,500, and I'm going to increase it by 5%. So again, finding 105% of it. So 5%, 10,500 is now $525. So this will increase by $525, okay? Now I could do the same in year 3. Start with what I had, 11,025, and I want to find 105% of it or increase it by 5%, okay? And if I do that, I now have $11,576.25. So you can see in the first year, it increased by 500. Then in the second year, it increased by 525. Now it's increased by $551.25. So it's increasing at an increasing rate. And that's what's happening with exponential growth, increasing at an increasing rate. Now, if I wanted to find how much money I'd have after 20 years, I don't want to go and do all these calculations. That would take forever. Note what I'm doing is I'm taking my original amount and I'm just increasing it by 5% in this case. And the number of years for which I've invested it is the number of increases. It's the number of times I increase by 5%. So after 20 years, I can just take what I started with. I want to increase it by 5% 20 times. So I want to multiply by this 20 times, which is why I have to the power of 20. So I can just put that on my calculator and the answer I get is about $26,533. Doing that formula much quicker than doing this process. So note, after 20 years, you can't just go 20 times 5 equals 100% and then increase 10,000 by 100%. A lot of people are making that mistake. You can't do it. Why? Because this isn't simple interest. It's not increasing by the same number each time. It's increasing by an increasing amount, as we saw here. The amount by which it goes up increases as well. So you have to use this formula. So the general formula, we just generalize what we did. So the amount I have after however many years is the amount I started with, times 1 plus whatever the interest rate is over 100, and then to the power of n. So here, this formula is the formula for compound interest, but I can use it for anything that grows exponentially. Anything that grows at the same percentage each year. For instance, if the population of a town was increasing by 5% each year, I can use the same formula. So that's the growth formula. Now, if it's decaying, if it's decreasing each year, it's a very similar formula, except instead of a plus in the brackets, there's a minus. The reason for that is, let's say I wanted to decrease by 5% each year. That's the same as finding 95% of the amount each year. And 1 minus 5% gives you 95%. Okay, so make sure you know these formula. Again, you can use them for simple interest, but you can also use them for other applications of exponential growth and decay, and I'll do an example of this. So just so we're 100% clear, note that P is the principal or the initial amount. Okay, R is the rate, and N is the number of increases or decreases. So that's what I mean with the arrows there, number of increases or decreases. And A is just the amount. Let's go and do a couple of quick examples. So here we'll do another example of compound interest. So I invest $20,000, 2.5% per annum or per year, and I'm doing it for 6 years. And we're going to find out how much I will have in my account if the interest is compounded annually, and then if it's compounded monthly. So if it's compounded annually, note compounded means how many times they recalculate the interest and add the percentage on. So they could do that, daily, monthly, yearly, whatever. So let's just look at compounded annually. So here I've invested $20,000, so that's my initial amount. The rate is 2.5% per year. And if it's compounded annually for 6 years, that means the interest will be recalculated 6 times. It's going to be increased 6 times. So I just use the formula. A equals P times 1 plus R over 100 to the power of N. Okay, and you can put that straight on your calculator and you get about, so I'm going to round it to the nearest dollar, 23,194. So that's much quicker than taking 20,000, adding 2.5%, and then doing that process 6 times. Thank God for the formula. So what if we compound it monthly? Well, the initial amount is still the same, but the rate was per year. If the interest is going to be recalculated each month, it's not 2.5% per month. You have to divide the rate by 12 because you're getting 2.5% every year, which means you're getting about 0.2083% per month. So just write PM for per month. Now, in this case, N, again, it's the number of times that interest recalculated, the number of increases, but it's not 6 because I'm compounding, I'm increasing the amount in the account. I'm recalculating the interest 12 times each year for 6 years. So N will be 6 times 12, which is 72. And that is the number I need to put on the formula. So once you've worked out P, R, and N, it's exactly the same as what we just did. So it's P times 1 plus, so R here was 0.2083. It was actually 3 recurring. That's why I put the dot there. So you need to divide that by 100 still. A lot of people forget to do that if R's, less than 1. And then I'm raising that to the power of 72. And again, I just put that in my calculator. So if I put that on my calculator, the answer I get is, to the nearest dollar again, 23,233. So you can see it's slightly more than if I compounded annually. So just make sure if you're doing compound interest questions, you've got the R and the N correct. I'm now going to show you an exponential decay question that has nothing to do with interest, so I can show you how to use the formula in that situation. All right, let's do this question. Population of a town, 40,000, decreasing by 2% each year, and we're going to use the formula to find the population in 25 years. So you might be tempted to say, okay, 25 years times 2% equals 50%, so the population will decrease 50%. Not happening. That's not how exponential decay works. So I showed you that in exponential growth, the amount the number increases by increases at an increasing rate. So if you invest $10,000, your investment increases at an increasing rate. So with exponential decay, in this case it's decay because we're going down each year, the number of people leaving the town is going to reduce each year. This number, 40,000, is going to decrease at a decreasing rate. It's not going to be the case that the same number of people leave the town each year. So that's why I can't do this business. Don't try to do this any differently. Let's use the formula. So we've got the amount, that's what we want to find, equals P. So that's the initial amount. It doesn't matter that we're not talking money here. P is 40,000 times. So now we go not 1 plus R over 100, but 1 minus R over 100 because it's decreasing. So that's what I went through on the other slide. So it's decreasing by 2% for 25 years, so it's going to decrease 25 times. So that's all there is to it, and we simply put this on our calculator. And so the answer we get to the nearest whole number, because we're talking about people, is about 24,139. So just so you know, that's of course more than half of 40,000. That's why this is wrong. So the percentage it's actually decreased by, it's gone down by 15,861 people. I can just figure out what this is as a percent of the original. And if I want to convert a fraction to a percent, I just times by 100. And so the answer I get is 39.6525%, okay? So this is the number of people that have left the town, because it's 40,000 minus 24,139. So that means the population has decreased in total by 39.6525%. It hasn't decreased by 50%. So it's decreasing at a decreasing rate. So that's how we can use the formula for exponential decay for an example not related to interest. So now we're just going to quickly go through similar triangles, which I know you've done in Year 9 as well. Let's now look at similar triangles. So remember that two triangles are similar if one is just an enlargement of the other. So they're basically the same shape, the same type of triangle. One just has longer sides. So for two shapes to be similar, all their angles have to be equal. Pairs of corresponding angles must be equal is the precise way of saying it. And pairs of corresponding sides must be in proportion. But remember, for similar triangles, we don't need to test every side and every angle. We just need to follow one of the tests. So AAA means angle, angle, angle. If two triangles have three pairs of equal angles, then they must be similar. Of course, you only need to show that two pairs of angles are equal, because if two pairs of angles are equal, then the third pair will also be equal, because angles in any triangle add up to 180 degrees. So that's the first test. The other test we have SAS, so two sides in proportion and the angle in between. If you're using SAS, it must be the angle between the two sides that are in proportion. So the other tests, we have SSS, which means all sides are in the same proportion. And RHS, if you have a right angled triangle and the hypotenuses are in proportion and another pair of sides is in proportion, they are similar. So to prove that two triangles are similar, you're always using one of these tests. So let's look at the two triangles here, ABC and also DCE. Okay, we'll get the vertices in the right order at the end. So are these two triangles similar? Well, to show they're similar, we need to use one of these tests. So we don't have any information about the lengths of the sides, so we can't use any of these three tests because they all involve showing that sides are in proportion. So I know that these two angles here are going to be equal, they're vertically opposite. So you need to remember a bit of geometry and angles in this. So these two triangles, it turns out, will be similar if and only if AB and DE are parallel. Only if AB and DE are parallel will this angle here and this angle here be equal, because they are alternate. And similarly, this angle and this angle are alternate. So I need to be told that AB and DE are parallel before I can prove these triangles are similar. So now that you know that AB and DE are parallel, let's go and prove that the two triangles in the picture are similar. So when you're asked to prove that they're similar, you have to say, you know, these sides are in proportion and give a reason, or these angles are equal and give a reason, and that's what I'm going to do now. So angle ACB, which is this one here, is equal to this one here, which is angle ECD, and I can abbreviate here. They're vertically opposite, just write vert op. Okay, so now that I know that AB is parallel to DE, I can say this angle and this angle are equal. So angle CAD equals angle CED. And the reason is they are alternate. So I've got to have that reason in brackets, otherwise it's not a proper proof. So because those two pairs of angles are equal, I know that this angle and this angle must be equal as well. I already knew that because they're alternate, but I can just say therefore angle ABC equals angle EDC, and I can also write rule of 180. So they must be equal. If two pairs of angles are equal, then the third must be equal. So I then, after I've shown one of these tests, in this case I've shown the AAA test to be true, I need to write a concluding statement. So I'll say therefore, so the first triangle you can call whatever you want. I'm going to call it ABC, is similar to, you can write it like this or you can write it like that, doesn't matter. Triangle, now I have to get the vertices in the right order. So A corresponds to E because there's that equal angle there. So I wrote A first in the first triangle, I write E first in the second. B corresponds to D, C corresponds to itself. So ABC is similar to EDC and AAA is the reason. So because they are similar, I know that all sides or pairs of sides will be in proportion. I just don't know what the scale factor is. I don't know whether the top triangle has its side lengths double the side lengths of the smaller one, or the top triangle sides are triple the length of the ones in the smaller triangle. I don't know. So you need to be given information for that. So let's say this side was 12 and this side here was 6. Then the scale factor is 2. So if I told you that this side here was 14, this side here would be 14 divided by 2, which is 7, because this side and this side correspond to each other. Okay, if I told you that this side here was 8, then BC, this side here would be 8 times 2, which is 16. So just make sure you understand, if you want to find a side in the larger triangle, you do what I just did, you times by the scale factor, and if you want to find a side in the smaller, you divide by the scale factor. So if I haven't made it clear, the scale factor is, in this case, 12 divided by 6. So it's the side in the larger triangle divided by its corresponding side in the smaller triangle. And that's why in this case it was 12 divided by 6, which is 2. Okay? So if you said the scale factor was a half in this case, you wouldn't be wrong. I just always tell my students to stick to this larger triangle divided by smaller triangle, just so we can use this rule without any confusion. So you always times by the scale factor to get a side in the larger triangle and divide by the scale factor to get a side in the smaller triangle. So that means that your scale factor should always be greater than or equal to 1 if you want to use this rule. Okay? Because it's always side in the larger triangle divided by a side in the smaller triangle. So I know that there was a lot to this video, and I did go through similar triangles in particular quite fast. If you have any questions, please let me know. Best of luck for your in-class project, and feel free to email me if you want any revision or you want any extra help, because I want you to do well, and I know you can do well. This has been the luckiest maths teacher in the world. Have a great day.